Good morning. We were discussing about single purpose processors or single purpose chips, single purpose computers, now which are very tightly bound to a particular application. On the other extreme, we have got the general purpose processors, where we have got immense flexibility. So, in between there are application specific instruction processors, but also we have got another variety which we were discussing in the last class, that is FPGAs or field programmable gate arrays, right. Now, the FPGAs are successors of programmable logic devices, PLDs, which appeared initially as array of gates, right. So, in the last class we had talked about an AND array, all right. Suppose each of these, on this plane we have got the AND gates, and on this plane we will have the OR gates, and I can program these interconnections. So, these means the wire, one wire is going like this, another wire is going above this. Now, if I establish a link between these two, they get connected, right. So, although it is showing that they are intersecting, they are still now not intersecting, but I can make them connected by some switch, right. If I connect them, then this point gets connected, this point gets connected, all right. Now, we can, when we talk about programmability, that programming is essentially in establishing such interconnections. As we had discussed that we can implement any logic function with AND, OR and NOT, right. So, therefore, I can have a canonical form of a Boolean expression and divide and write it down as a sum of products form. So, the products are essentially the ANDs and the sums are the ORs. Therefore, I can implement a Boolean function using that. Now, that has been further extended to much more powerful FPGAs, where we have got the possibility of configuring different logic circuitry on a single chip. Now, FPGAs, before going into the details of FPGAs, we will discuss about some basics of digital logic that we had all of you have done at some point of time. Now, all of you know that NAND gates are universal gates. So, you can implement any logic function using a NAND gate, similarly with NOR gates, right. Now, if I say multiplexer is a universal gate, would you agree? If I say multiplexer can act, I should not say is a universal gate, but Marx can implement any logic function. Is it true or false? It is true, because say I have got a 2 input or say 3 input Boolean function. So, 0 0 0, and I will have some output . So, I will have 1 2 3 4 5 6 7 8 combinations, and corresponding to each of these combinations, these are the input combinations. This is the input, corresponding to this input combination, I will have different outputs. Say my output is something arbitrary, I am writing 1, 0, 0, 0, 1, 1, 0, 1, say, implementing some logic function. So, I have got 3 inputs and I have got ones and zeros, 8 possible outputs. Now, if I select a multiplexer, with these input lines serving as 3 control lines, right, C0, C1, C2, all right, C0, C1, C2, and all these 8 outputs coming as, all these coming as 8 input lines, 4, 5, 6, 7, 8, 8 input lines. Now, I can put in this as 1, this as 0, this as 0, this as 0, this as 1, 1, 0, 1, and here is my output line. Now, depending on whatever the input is, if the input is 0, 0, 0, that means this input line will be propagated to the output. So, I will have the output to be 1, if this be 0, 0, 0. If this be 0, 1, 0, if I make it 0, 1, 0, the control lines, that means the third input will be propagated to the output. So, then this will become 0. In that way, any truth table I can implement using a multiplexer, right. This is one of the concepts that we will be requiring while we work with FPGAs. Yes, of course, depending on, if you want to minimize that, if you want to, once you do the logical minimization, then you can certainly do that, okay, you can transform it. But this is a straightforward implementation, when here of course I have not thought of any optimization. The other possibility could be that suppose these inputs are essentially address lines. Suppose I have got an 8 location memory, just 8 bit memory. Okay. So, I have got a memory, single bit memory with 8 possible locations. So, memory M. Each location has got single bits, 2, 3, 4, 5, 6, 7, 8. Now, just like here, I can have these ones and zeros stored in this memory location. I can have it 1, 0, 0, 0, 1, 1, 0, 1, and these input lines, for 8 locations of the memory, I need 3 address lines. So, if I have these 3 address lines coming up here, say the address lines are 3, where the input is coming in, and from here I establish a decoder, and that is selecting any one of these locations depending on this combination, and I will read from that location. So, if it be 0, 0, 0, then I will get 1. If it be 0, 0, 1, then I would be getting 0, like that. So, the same thing can be used using this sort of memory, which we will call as lookup table. Okay. So, as if we have got a table where all the outputs, possible outputs are stored in the proper combination of the input, then as that input arrives, I will get that output. Clear? So, that is also another way by which we can implement the combinational logic. So, by this or by the mux or by this lookup table, I can implement the combinational part of the logic. Okay. Now, in the last class, we had seen that an FPGA is nothing but, I had drawn a diagram where I had shown that there are a number of configurable logic blocks. Suppose we have got such an array of logic blocks, each of them is known as a CLB or configurable logic blocks, and they are surrounded by a number of lines. I am just showing one line, but it is actually much more. All right, through which I can establish interconnections. Besides that, now I will establish interconnections along these lines, and around this entire chip we will have the inputs. If I just draw a boundary of this, then I will have the inputs coming here, the input ports, the output pins will come out from here, all right. There will be clocks and all those things will be coming in around this. We will show that in a second. Now, one of the interesting features of such FPGAs is that by establishing the interconnections of these configurable logic blocks, I can establish different functions. Consequently, what can happen is that I can divide one FPGA into a number of slices. Maybe this slice is implementing some logic 1. This slice may implement another logic, for example, say it is establishing a logic like this. All right. And this slice is implementing another logic, some logic is coming here. Maybe I am implementing an XOR. Now, the point to note is, since the same chip, different parts of the chip can be assigned different functions, I can implement them, they can all act in parallel. Therefore, I can get some speed up. On the other hand, if I look at general purpose processor, typical sequential general purpose processor, where I am executing a C code, that C code will be sequential, and any hardware for that matter can be executed in parallel if I have got parallel data paths activated through the controller, and the same can be achieved within an FPGA. Okay. So, quickly collecting up the things that we have discussed till now, we will have established this interconnection of the programmability will come from this interconnection, right, and we will take help of the basic phenomenon of this basic power of multiplexers as well as the lookup tables or the memories. Okay. And we will establish interconnections through this. Now, so these are the now interconnections. How do you carry out the interconnections between this? Establishing interconnections. There are different techniques for establishing interconnections. One is antifuse, another is known as SRAM based. Okay. Now, antifuse, so what do I want to do? I have got one wire like this, another wire like this. There are two different colors, and one is they are not connected. I want to establish an interconnect. So, I can have a connection established here, right. How can I establish it here? In antifuse, what is done is there is a conductor, one part of the conductor is just like a switch, right. If I close this switch, then these are connected. If I open this switch, that is not connected. So, I have got two pieces of conductor, and in between there is an insulator. Therefore, this part and this part are disconnected, right. Now, if I apply voltage, this insulator actually breaks down and this becomes conducting. Therefore, by applying suitable voltage, I can make it conduct and I can establish the connection between them. All right. A fuse wire, what happens? When high current goes, the fuse wire snaps. Here, when I apply this, it actually joins these two. That is why it is called antifuse. Okay. This is one way it can be done. Now, antifuse technique, since I am just like a fuse wire, if it snaps, you have to replace another wire, right. Similarly, in antifuse, if I antifuse it, if I establish the connection, that is permanent. So, I cannot at will change it, remove the connection or establish the connection. On the other hand, the SRAM based thing is something like this, that here between these two I have to establish a connection, and I have got a transistor here. All right. Now, if I apply a 1 here, then this transistor will conduct. So, these transistors are known as pass transistors. All right. And whether I will give 1 or 0, that this pattern I can keep in some sort of a 1 bit RAM, right. So, this is programmable. I can write a 1 here or a 0 here. If I write a 1 here, then this pass transistor becomes conducting. Therefore, any signal that is coming through this path will go through this path, right. And if I make it 0, then obviously this connection is snapped. Therefore, such interconnection is programmable. At will, I can establish the connection or can withdraw the connection. So, SRAM is very popular and used. Antifuse is of course not programmable, but that is another way we can establish the interconnection. Given this background, we will now move to a discussion on FPGAs. And this part of the lecture, I will borrow heavily the slides from Dr. Konstantinos Tatas, taken from the internet of course. Here is the acknowledgement. You can also find the slides in this site. Okay. So, we will briefly look at, I told you in the last class that there are two major manufacturers of FPGAs, one is Xilinx, another is Actel, all right. There are others also, and Xilinx itself makes different varieties of FPGAs. So, one of the FPGA board is just like a board. Here you can see this, right. It is a board, it is a Spartan 3 board, where you can see the FPGA here, it is a chip, this is the FPGA, all right, and this is what will decompose it, we will break it up soon, but right now this is a chip, and here you can see we have got so many things. These are some LED array, there are some LEDs. Here these are some switches, okay. These are some switches we can set. Here you can see the input output pads. This is a connector with which I can connect to the other outer world. And in the present we have got much more complex FPGA boards being made now, which are which have got some signal processing activity, some memory, all those things come up over here, all right. So, this is one typical board, and I would like if you do some development on such FPGAs. Now, let us start our journey. Here is the FPGA. Now, what is there inside it? Now, depending on the complexity of the FPGAs, the inside will vary, but a typical FPGA structure is as shown here. The red ones are the configurable logic blocks. So, here I am showing 4 configurable logic blocks, and as was shown in the earlier diagram, that there are wires all around, going all around, like this. The wires are going all around, and I have to establish the wires. In order to establish the connection, we are given some switch boxes, we call them switch boxes, which are here, all right. These are interconnection networks, and there are I/O signal pins. That is the overall layout with the 4 CLB system, all right. Now, what is there inside a CLB? This is clear? So, we have got the switch boxes and the CLBs. Now, what is there within this CLB? If I take one CLB and blow it up, we will find that there is a very simplified CLB, very overtly simplified. Actual the CLBs will be a little more complicated. Now, let us try to understand what is there. We have got a lookup table, which we call LUT, lookup table. and we have got inside a CLB say a D flip flop. Now, and there is a multiplexer. Okay. So, whatever logic I implement, we will soon implement a logic. Whatever logic we implement, we can implement it through the lookup table. We have explained a couple of minutes back, and the output of that lookup table I can directly take out, or I can take it at the next state. Therefore, I can put it at the D flip flop and it can be remembered in the D flip flop, right. And all of you know that the D flip flop will have whatever is the input now will be made available at the output after 1 clock delay. So, I can establish a delay by this. So, and I can activate the control of this multiplexer to either select this input or select this input, any one of them can come, all right. Is it clear? Let me hold it for a while, so that those of you who want to draw it can draw this. This is a lookup table, and we have seen what a lookup table is. A lookup table can contain the ones and zeros as we are showing there, right. We are showing a couple of minutes back what a lookup table contains. So, it was like this, a lookup table where I can put the inputs and the output of that table will come out, right. Okay. So, given this, the same diagram, you hold on to this diagram and we will try to implement one simple, very simple logic function, that is a 4 input AND gate using this. Simplest possible 4 input AND gate. How can I implement the 4 input AND gate? Simplest possible logic function, A and B and C and D. So, I have got these 4 inputs A, B, C, D, and here is a truth table for that. For all 0, 0, 0, 0, 0, I will have 0, 0, 0, 0, 0, 1 will be 0. Only when everything is 1, I will have 1. That is the logic function of a 4 input AND gate. Now, I have to gate this through my CLB. Suppose this I want to do through only one CLB. I will just need one CLB to do this. And what do I have within this CLB? I have got a lookup table and a D flip flop for this simple CLB, right. So, now if I feed A, B, C, D as the address of this lookup table, and this lookup table is programmed to have only this bit to be 1, it is probably not visible, all these are 0, 0, 0, 0, only this one is 1, because here only this one is 1, this is the output combination, right. I program this with the desired output with respect to these given inputs, and I take that output here, that output will come out through this, and the output will also be available at the input of the D flip flop. Now, as an AND gate, it is a combinational circuit. Therefore, the output will immediately follow the input. So, whenever these inputs come, this lookup table will feed that particular 1 or 0 over here, and then I will have to select this path from the multiplexer. Therefore, I have to feed this multiplexer with a 0. Clear? Not clear? So, let me once again do this. Good that you said it is not clear. So, I want to implement a gate 4. let me say I'll even make it simplified. I'll make it 3 input gate, 3 input AND gate, and the output will come. So, what is the desired what is the combination? 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1 8, and I will have the outputs to be, it is an AND gate. So, only one will be, all the inputs are 1. So, all these will be zeros. This will be 1, right. Now, I just take this and feed it, program it in the lookup table. Lookup table. So, the lookup table will now have 0 0 0 0 0 0 0 1, right, and at my input will be whatever the logic input is. These are A, B, C. So, they are coming in here. Obviously, I am showing it directly coming here, but they are just coming as an address. So, it will be coming through a decoder. So, A, B, C. So, what will be the output of this? Some bit coming from here. Now, this one I want as an output. I wanted an output, and what does an AND gate do? AND gate is combinational. So, whenever this pattern say 0 0 1 appears here, immediately the output should be 0. If this changes to 1 1 1, it should immediately change to 1, no delay, no delay at all. Therefore, this is coming to the multiplexer, giving me a choice of either selecting this, or this is also coming through a D flip flop. With the clock input, and this is also coming here. Now, I have got the choice of either selecting this now, or I want to have it 1 clock later. What would I like to do? Now, I want it now. Therefore, which input would I select, this or this? I would select this directly. In order to select this, what should I feed at the input of the multiplexer? I should feed a 0. Had I given a 1 here, that would have meant that this is going, this is being selected, and as soon as, whenever I gave, say for example, I gave here 1 1 1, then my output is 1, it has come here 1, but if I make this 1, what will happen? I have made this 1, it will be 0 till the next clock, right, but I want it immediately. So, this one I want here immediately, therefore, I make it 0, clear. Therefore, in order to get the logic circuit, logic function implemented, what I needed is 2 parts of the programming. What are those? One is configuring the lookup table and configuring the multiplexer control, right. So, these are known as the configuration beats, all right. One part of the configuration bits, how I configure the CLB.
So, why would we need the multiplexer in place when the lookup table is already doing the job of?
Because sometimes I may like to have it, I can also try to implement some sequential circuits using it. So, that I may like to put delays, I would like to memorize this here, all those things I can do using this D flip flop. But right now for this simple AND gate, I do not need this path at all. So, I am bypassing that. How do I bypass it? Making it 0. Okay. So, now after having a brief look at the configurable logic blocks, Now, we will have a look at the interconnection networks. Here we are trying to amplify one particular switch box. What is being shown here is a number of switches are number of lines are coming in this way, and there are several possible intersections, right. There are many other intersections here also. At each intersection, how many possible routes are here? How many possible routes are here? You can connect this to this, you can connect this to this like that, or you can connect diagonally. For example, so I have got, so I will just make it a little larger. I have got the way of connecting these two, A, B or B, C, A, D, C, D, B, D or this. Therefore, at each of these junctions, if at each of these points 1, 2, 3, 4, 5, 6, each of these points, if I put a pass transistor with a 1 or 0, say any 2 points, say this is A, this is D. If I make it 1, that means A and D will be connected. Similarly, for this between A and C, I will have a pass transistor. If I make it 1 and 1 or 0, accordingly A or C will be connected, right. Similarly, for this, here I will have another pass transistor, clear. So, I have got this switch matrix here, where here what has been done, I have made this to be 1 and all others are zeros. That means, which 2 points are connected? This point and this point is connected, others are not connected, right. Thereby, I can establish the interconnection between these. So, for this switch box, what is my program? My program will be 0, 0, 0, 0, 0, 1, right, 6 bits because of this 0, 0, 0, 0, 0, 1. If I make it, then this and this are connected. If I make it 1, 0, 0, 0, 0, 0, that means this and this are connected, right. Am I clear? Thus, by programming, I can establish interconnections at my will.
For every interconnection junction, in that case you will need 6 lines, configuration lines coming.
Whenever if we look at the array, then here I have got the lines coming, right. Now, I may like to that the connection is in this direction, or the connection is in this direction, or the connection is in this direction, or the connection is in this direction. So, for each junction, in this case, I am needing 6 such switches, okay, because of this sort of possible interconnections. Okay. So, I am requiring 6 bits here, just for this sort of, you can vary the type of interconnections. Okay. So, tomorrow we will take up another example that we will be programming with FPGA and proceed with further details.